of how. And for your generation, us old timers who've lost our hair, even if we got ponytails, it's a real testament. Because we do understand that the issues we're dealing with collectively, as communities, as individuals, people who love the Great Lakes, love the natural resources that make this part of the Great Lakes so special, we recognize there are a lot of issues that need to be dealt with. And you're helping us get the data. So scientists, we need that data and telling those stories. So I'm going to be quiet, but kudos to all of you, to your faculty. Amy Lentz from LNRP is also here, our director of projects. Take it away. I can't wait to hear what you've done. By the way, I saw them out in the field periodically, rain or shine. They were out there collecting samples. So kudos to all of you. Thank you, Rick. Thank you, Rick. Yep.
And one more of our really important collaborators is Russ. And Russ represents a group known as Friends of Pika Bay.
Friends of Pika Bay, yes. Representing Friends of Pika Bay. It's a small group here in southeastern Wisconsin. Trying to focus on some invasive species issues and water quality issues. Again, thank you all for attending. I did see a practice section of what you're about to see, and I know you're not going to be disappointed. And this project, as mentioned, goes back a long ways. The DNR removed the Prepid Dam in the village of Cleveland on Centerville Creek in 1998. And when that was removed, 100 years of muck started entering into Lake Michigan. And the Lakeshore Natural Resource Partnership, working with the village of Cleveland and with UW Green Bay professors, began developing a set of options for the restoration of the creek in 2009. The creek restoration project has been implemented in several phases, but an important part of that project was testing to see if restoration projects really can make a difference. The intern testing provides the data to test restoration results. And I've had the pleasure of working with interns since that first summer, as mentioned, with one intern and 3 sites to 9 interns, 4 sites, and 29 different spots, rain or shine. And the work ethic of this year's interns is quite amazing. Thank you. Their ability for working collaboratively is exemplary, and their attention to detail has made the science that you're about to hear solid, and over time has provided results and changes to land practices. The University of Wisconsin system has been guided by the Wisconsin idea since 1904, holding that a public university should improve the lives of people beyond the borders of its campus. This project demonstrates the university is not just a campus in downtown Manitowoc, but is a living part of our community, bringing science back home to residents. A special thanks go to Rick and Becky for their mentoring and dedication that they freely give their time every summer, making this research possible. And also, the testing would not be possible without the funding and resources from the Lakeshore Natural Resource Partnership. Representing them tonight was Ralph and Amy Lentz. We thank them for their support. And we miss, normally Jim Kepler would be here. It's an integral part of the project, but he's home ill tonight. So this year's future scientists will introduce themselves. And they ask that you hold your questions until after the presentation. Questions are really important. There are no silly questions. There are all good questions. They want to hear them. So with that, here is the 2023 Stream Team. So
So thanks all for being here. I'd like to welcome you again to the 2023 Water Summits. We are the UW Green Bay Manitowoc Stream Team. I'm Chris Santiago. I'm majoring in environmental policy and planning, and I'm going to hand over my invisible mic to my colleagues to introduce themselves.
I'm Sam Fromfeld. I am a bio major emphasizing in ecology and conservation, and I am double minoring in chemistry and environmental science.
My name's Elena Damian and I'm majoring in animal biology. My name is Taylor Kelkser and I'm majoring in environmental science and minoring in chemistry. My name is Elena Zavala and I'll be minoring in cognitive science and minoring in computer science. My name is Natalie Ford and I'll be majoring in environmental science and minoring in chemistry.
My name is Cody, and I'll be majoring in either environmental science or biology.
I'll take my invisible back. Thank you very much. So we do have, as mentioned before, one other colleague that's not here with us today. No, she's not passed away. Don't let that thought go through your head. But listening is another vital asset. There's some phenomenal work as part of our team. So we just got you through the who, we're gonna get you through the what, where, why, how. So why do we monitor? We want to see how pollutants affect our streams and observe that impact on local areas. So we know that every little bit that goes into these streams is going to build up and it's all going to go out to Lake Michigan. And we want to make sure we're lessening that impact that we have and keep things healthy. In addition, what we do is going to influence the TMDL, the total maximum daily load. Basically, how much phosphorus is actually allowed from where to go at, and how can we control it. When and where we sample, we have 4 wonderful streams that we go through, and we sample every Monday. In addition to any time it rains a ½ inch or more. Rain or shine, as mentioned a couple times already. Now, the reason why we look at these streams is because we want to see the effect of different land use. We're looking at our more urban environments, such as Little Manitowoc, or our more rural environments, such as Centerville. In addition, there are sites that we are going to highlight later on that are very key as they are right before it goes to Lake Michigan, and potential restoration points in addition to ones that are restoration points in there. Just wait for that to register unless it doesn't want to. There we go. So how? Well, we use field equipment that we then use in the field and bring back to do additional tests. The first of which, a meter stick. It measures depth. Who would have guessed? In addition, it actually is going to be used for a calculation later. That is my baby, which is the phosphorus load. Now we have another piece of equipment called a DO meter. That stands for dissolved oxygen. We want to save our own oxygen in our lungs, saying that. And wonderful technology actually measures 2 things. 1, temperature. A higher temperature can increase the amount of stress on organisms in the water. In addition, temperature is going to have its effect on our DO. So to make it simple, increased temperature means decreased DO. Lower temperature means increased DO. In addition, eutrophication, plants growing and decaying, in addition to ecology, is going to cause fluctuations in our DO as well. We also have this wonderful flow meter that's right here, and the flow meter measures flow. How fast is the water moving in feet per second? So with rain or drought, with droughts there's no flow, but with rain or drought, it affects the speed of our streams. In addition, high speeds will increase our DO, erosion, and the movement of substances that are in the water. Lower speeds mean stagnant pools and the buildup of these materials. So I mentioned bringing back this water for lab tests. So one of them is turbidity, basically the suspended particles that are in the water. How clear? How murky. And with those particles, there'll be an attachment site for pollutants and nutrients that are brought into that water. In addition, it will block sunlight and affect plant growth. Sunlight's not getting to our plants, they can't grow. And we'll move to pH. most of you probably know what pH is. It's the acidity of our water. And we have a wonderful threshold that we want to keep at, which is between 7.2 and 9.6 to the first. Now, ammonia and nitrogen is a fun one because we get this beautiful green here. We don't want it that dark and green, but this is a visual indicator that we see in our tests as ammonia and nitrogen are essential for organism growth. Too much is harmful though. Now, we can measure NH3 from this, which is toxic to most fish, and NH4+. When that is broken down, it turns into NH3 and becomes harmful. Now, this is introduced by fertilizers, manure, sewage, and decomposition of plants and algae as well. This is a fun one as well, E. coli. Most of you probably know about E. coli. When we look at this, we have E. coli as an indicator to figure out just how much fecal contamination is in our water. The reason why we want to establish how much is in and measure that is because it determines whether or not the water is safe for recreation. Can you swim in this water? Now, we have a reagent that we use that we add to our water, incubate it, and when we put it under a UV light, if it glows, that means we have E. coli. That reagent is actually going to promote that growth. And as you can see here, all of these boxes are glowing. So there is tons of E. coli in the water sample from this. Now there are surface water standards, 0 to 234, it's open, swim in it freely. 235 to 999, this is advisory, please shower after being in this water. I don't know why you wouldn't in the first place. And lastly, anything over 1,000 is closed. Do not enter this water, do not pass go, do not collect $200. But in all honesty, I mean it. Do not go into this water. And you probably shouldn't let your pets in it either. Now, here's a big one. Phosphorus. This is a limiting factor of eutrophication, which we have mentioned earlier. And phosphorus can increase in our streams by the effect of rain events. The rain comes down, it picks up some of the sediment, dirt, sand, anything along the way, which is why we talked about turbidity, and brings it into the stream as it's attached to those particles. The way that we measure this is through absorbance levels. We take the water, we add our reagents or appropriate chemicals, and through our process, this water will turn blue. The basic idea is that the darker the blue, the more phosphorus is there as it's an indicator of it. We then put it into a wonderful machine with a long name called a spectrophotometer, $7 name, and it shoots out a wonderful number at us, which we can use to calculate total phosphorus and total dissolved phosphorus. Total phosphorus is total phosphorus. It's literally what is all there. Meanwhile, total dissolved phosphorus is going to be what is readily available for the environment, plants especially, to use. We do have a water standard, which is a concentration number of less than 0.075 milligrams per liter. Now we get into my baby. Love this one, sorry. Now, phosphorus load. What is phosphorus load? Whereas we have the concentration that I just talked about, phosphorus load is how much is actually being moved. So how do we get this? We combine a number of different elements, which being the flow, depth, both along the width of a stream evenly, and combine that with the concentration that I just talked about, and we can get the amount of pounds, because we're American, the amount of pounds that we see go into Lake Michigan every day. It is a snapshot so that we know it's not exact amounts, but we get a strong idea. And just to kind of make your mind think a little bit more, a pound of phosphorus can make up to 500 pounds of algae in the water. That's a lot, honestly. So the last thing I really want to touch on before I hand my invisible mic, don't forget about that over, is quality assurance and quality control. QA, QC to save DO again. We have separate tests, which is what this is, that are designed to make sure our techniques are consistent and that our reagents are doing what they should. This is a Wisconsin DNR approved protocol. And the way we do it is we choose a random stream each week, take our 2 sample bottles and at the same exact time, get that water. What this does is we can then take it, bring it back, and it is used to assess whether the differences we see are due to water variation or technique errors. What this also means is that all the data that we are going to talk about today is correct and reliable. So I'm gonna hand this invisible mic over and actually my laser pointer that's saying to talk.
Okay, we're gonna be talking about Centerville Creek, which is located down in Cleveland, 15-ish minutes from here. I'll be focusing on the phosphorus portion of it, but first I'll get us situated. So our Centerville Creek consists of 2 different branches. So we have our northern branch up here and southern branch down here. Over on here, you see all these weird numbers and letters together. That doesn't mean anything to you. This is just all the locations that we sampled in Cleveland. And anything with this CN in the top, that's part of the north branch sample. Anything CS is south branch. And anything CR is part of our restoration, and that's right off of the Lakeshore there. Okay, here we're looking at average phosphorus levels upstream to downstream. We have those 2 different panels because there's the 2 branches for Centerville Creek. First of all, just to kind of orient us into what these graphs are showing. This green line here is our total dissolved phosphorus, which Chris recently said that's what can be taken up right away by plants and algae and stuff like that. And our orange line is our total phosphorus. That could be an issue if there's too much of it in the long run. Also, we have that DNR threshold line right there. As you can see, our 2 branches have different peaks at different areas in the branch. One at CN08, which is right in the middle. And we think that's because in Cleveland, a lot of the summer, there was lots of construction ranging actually from our CN10 site to CN08. And over in the South Branch, we have that peak right in the beginning of the stream. And that's, we believe, because it's right at the bottom of the slope of a hill. And gravity works to bring nutrients down into the slope. So first taking a look at that northern branch hotspot, again, orienting us in to the middle of our northern stream. I want to point out now on this graph, we have blue in the back, which is how our rain has been. So this is rain the week before leading up to that sampling day. And something that we found with our research this summer is that in the beginning of the year, for example, taking this June 26th, we had kind of a small amount of rain, a little over ½ an inch, and our phosphorus peaks way, way up. But then we go over to the beginning of August, and we have even more rain, and phosphorus is the same, if not lower than that beginning of the summer site. What does this tell us? If we look at this picture over here, all of that flourishing plant life, you know, end of the summer, plants are at their like peak of being able to take up nutrients, while in the beginning, you know, they're still trying to grow and build their, you know, basis. And this is super important for us when we're thinking about restoration activities, because now we know, well, this helps prove the fact that planting a bunch of plants in that restoration area can help lower those phosphorus levels, which is what we did at our restoration. It changed. Okay, now we're gonna look at that southern branch hotspot, right in the beginning of the southern branch. And we can see the levels are fairly similar to that CN08, that last slide's hotspots. But just to point out, this graph does go all the way up to 4.5. So we did have that one day in the beginning of August that phosphorus really, really spiked. Can't say for sure, you know, fertilizers are often being sprayed, but rains still have huge effects on the phosphorus levels. We've also noticed that this site is consistently kind of mucky, and there's a lot of potent smells at the bottom. So, you know, runoff, everything can really affect what's getting into that stream. Next, we're gonna look at the restoration area averages, which is right going into the lake. And this is what's really, really cool, because it's the first year that we've like seen this data. So we're going upstream to downstream here, CRO3, CRO2, CRO1, so in order. And it's kind of a wave as it goes closer to the lake. And what's really cool about this is we have all these rain events, and look at those levels of phosphorus. They're hardly changing at all. So this is extremely exciting because it's showing that our restoration is doing the job that we wanted to do. I will pass it on to you.
Thank you. So I'm back to talk about my baby here. Phosphorus discharge, very proud of it. So, as was just mentioned, we have all these sites that are coming from north and south branch that are going to converge at this point right here. And that's what this wonderful graph is going to represent for you. As you look at this graph, you are going to see that as the total flow of water in feet squared per second increases, we are seeing a phosphorus load increase. Remember what I said about a pound of phosphorus can create up to 500 pounds of algae? This is about 20 pounds of phosphorus a day. Now, that's right before it hits the restoration point. It starts to go through, and the whole point of this restoration point is to lower the amount of phosphorus, improve the quality of the stream, and slow it down. And just as Sam said, we get exactly that. And it is incredibly exciting because when we look at the following graph, which represents the point after the restoration, we are seeing not only did it level out, we are seeing that it lowered. And we are looking at less than 5 pounds a day and a much lower speed overall. That is just beautiful to be able to say. So that's all that I have to say here about our phosphorus discharge. But there we go. Always have to question it. It's important to know that the effects of the Centerville Restoration Project, that even though it's been in place since 2012, that there are many signs that it's working as we have told you here. Though it was initially expected to start showing signs of that improvement in 10 to 25 years, we are right in the middle of that. So phosphorus has overall been constantly lower at these restoration sites, even though rainfall was more variable this year than last year. I'd like to pass this mic on over to Lenny.
So now we're going to be talking about dissolved oxygen, or DO. So dissolved oxygen is basically the amount of oxygen in a body of water that's readily available for the plants and other organisms that live there. And dissolved oxygen is affected by a lot of things like temperature. So if it's a higher temperature, then it holds less oxygen. And if it's colder, then it holds more. Stream flow and atmospheric conditions also affect it, as well as photosynthesis and decomposition. So if there's a lot of photosynthesis happening, then that adds oxygen into the stream, and decomposition removes oxygen from the stream. It's important that we look at dissolved oxygen because if it reaches below a certain point, specifically 5 milligrams per liter, then it becomes stressful for the organisms that live there. Another thing that we're going to be talking about a lot is dissolved oxygen saturation. This is the concentration of oxygen in the amount of water. So if we see a percent that is very high, way above 100%, this means that the rate of photosynthesis has greatly surpassed the rate of decomposition. So if we look here, here is the average DO saturations for the northern branch of Centerville, so that's right here. And we see it's about usually from 50 to 100%, except we have these two peaks here at the very most upstream branch and down at our restoration site. And so at our restoration site, we see it's all between 100 to 100%, and it's fairly stable. But if we look at C11, we see these extremely high peaks in the beginning of the summer, and then it dropping down at the end of the summer. So these are photos from the first or second day. And you can see that there's algae and there's a lot of direct sunlight. This means that the photosynthesis rate is very, very high, which is why we have it at over 200%. We're also collecting this data at about 1 o'clock. So the rate of photosynthesis is also. If we fast forward to the middle of the summer, we see that our stream looks very different. There's weed and there's now duckweed, and it's about 80% covered by the surface. 80% of the surface is covered by the algae. But if we look at our graph here, we see that the saturation is about the same. And this is because with all this added plant life, there's also decomposition that is happening that is lowering the saturation. And then, so if we look at our graph, we can see a gap here, and this is because the stream had dried up. And when it dried up, the algae and the duckweed had died off. And so once the stream came back, the algae was still there, but the duckweed was no longer there. At around the same point, the grass had overgrown and kind of started collapsing over the stream, so it shaded it a lot. And so we can see this is near the end of the summer, and you cannot even see the stream. It's completely covered, and we have to like separate it to actually get our samples. So that is why now in this half, or like this end of the summer, the saturation is very low because there's no sunlight for the rate of, or very little sunlight compared to the beginning of the summer, and there's less plant life. Now, if we look at our restoration site, the stream in the beginning of the year and at the end looks very similar, and the rates were high for the same reasons with CN11. Even though you can't see the algae, there's algae underneath, and there's also a lot of direct sun that's allowing for that high rate of photosynthesis. And other features that help make the DO so high is because there's meandering and logs and ripples, which are specific techniques used in restoration sites to add to the DO.
Okay, so moving on, I would like to share some observations and research that we did over the summer for Pine Creek. Oh, I'm sorry. So starting off, originally stream team only sampled had 4 sites. Starting upstream had PIO5, PIO4, PIO3, and PIO2, which opened up in Lake Michigan. However, this year we added 4 new sites with the new 90 element plan, which involved PIO6 for phosphorus absorption, PIO7 on its lone branch for the buffer zone, and then PIO8 and 9 for the restoration. So the 9 key element plan's purpose is to lower phosphorus levels and sediment loads that are being released into Lake Michigan by Pine Creek. However, this project hasn't started yet, so all the data that we collected from these new sites and the original sites are going to be used as pre-restoration data by future stream teams. But that being said, let's get some phosphorus. So starting at our furthest upstream sites, PIO6 and PIO5, we see that PIO6 had the lowest numbers for phosphorus compared to the other new pine sites and stayed pretty consistent throughout all summer. And it was roughly the same with being lower and underneath our lovely little water standard line for PIO5. However, we couldn't collect enough data from the site since it kept drying up all summer. So not entirely sure if it would have stayed consistent throughout the rest of the year. As for PIO7, which is our Long Branch site over here again. We noticed that the dissolved and total were near each other for most of the weeks in the early part of summer. However, around the time of June 26th, we had 2 non-rain events that we didn't collect for because it was below 0.5 inches. But we ended up seeing that phosphorus spiked and then remained fairly high throughout the rest of summer, which is also something that we noticed at our other 2 new sites, PIO 8 and PIO 9. You can see they're fairly consistent at the start of summer before spiking around the same time. And PIO 8 saw that jump and stayed fairly high throughout the rest of summer before significantly decreasing towards the end of collection. Whereas PIO 9 saw a consistent level of phosphorus throughout the rest of the summer. We don't know why it spiked, but our only guess is because it was the first introduction of rain since we started collection. Which I'm gonna pass this to you.
So I might have lied to you. I have more to say about my child. If only I had a wallet to just let the photos roll out of for you. But I'm just gonna talk about very briefly the discharge in Pine Creek, because as we've stated, this is a site or area where these restoration efforts haven't been put in place. And when they do, it's going to take time to see that effect. And similar to how when everything converged on the previous site that I spoke about before it hit restoration, we are seeing that with the increased flow, we are seeing an increased phosphorus load that is not being controlled. This is very important because this shows that this area needs to be, or is a potential source area for future restoration efforts to be put into place. And now I'll pass this mic back on over.
Thank you. So before I get started, I do want to give a couple of minor benefits since we talked about dissolved oxygen. So dissolved oxygen is the amount of oxygen present in water and it's needed to support marine life. Anything below that lovely number is going to stress out the ecosystem and also can't support certain organisms in the water. And unfortunately, Pine Creek reached some very low numbers this summer. So starting out back with our Parsons Lake comparison, PIO 6 and PIO 5. PIO 6 had the lowest dissolved oxygen levels of any of the Pine Creeks this summer. Lowest reaching even below 1. So compared to PIO 5, which again are missing points because it dried up this summer, it also remained at consistent below 5 for the dissolved oxygen. Both streams are fairly stagnant all summer when PIO 5 was actually there, which we think kind of contributed to the low dissolved oxygen levels. But PIO 6 also contained a lot of dead plant matter and dead plants around the stream that we think also affected this. Moving on to PIO 8. We noticed that in the early part of summer, it had some fairly high dissolved oxygen levels, which is what we wanted to see, but it was slowly declining with every collection before finally hitting a drop off and drying up. After it came back though, we noticed that it kept a fairly consistent number at around 7 for dissolved oxygen, which is what we kind of want to see. But then looking at PIO 9 and 3, you can see this is one of our new sites, this is one of our old sites, and this is where both branches of Pine converge. So PIO 9 had some very fluctuating levels, either reaching below a DO of 5 or above it. And in part, we think it was very stagnant. It didn't flush out of the tunnel that much all summer because of rain. And it had a lot of overhanging dead plant matter and live plant matter, which could have caused the fluctuating levels compared to PIO 3, which had consistent flow and not much plant matter running in it. So even though it had that drop off, it remained fairly consistent all through summer and never went below 5. Which the reason I keep bringing up plant matter is because of our story PIO 7, which involves lawn maintenance. So PIO 7 is located between woods and private property and is located in a more rural kind of area. And some of the observations we made over summer was it's very overgrown downstream from where we sampled and very stagnant all summer and contained a lot of algae. So you can kind of see in this picture how overgrown it was most of summer. But the other thing we noticed was the long hair by the residents that were living on the private property right next door. So our first collection day on May 29th, we noticed that the stream down to the water and all that dead plant matter and grass was either laying right next to the stream or was laying on the stream itself. And then the next week on June 5th, when we went back, it was cut right down there again, but with all that overgrowth, it was catching and staying kind of in the same area. However, about mid-July, the residents started cutting the grass farther away from the stream and allowed a natural buffer to grow in between the stream and the grass cutting itself, which you can see the impact with our data that we took this time. So the red dots represent when the lawn was cut to the stream, and the green dots represent when there was a natural buffer left between the two. So start of summer, we see a sharp decline in dissolved oxygen before it rapidly went down below that 5 threshold and stayed kind of around there, had one little jump just barely above 5 though. But once we noticed that the stream had that nice natural buffer kind of left between where the grass was being cut, we saw that it leveled out most of summer, roughly being above 7, and was able to keep that consistency even though the grass was cut again later on in summer down to the stream. Why should we care about this though? So lawn and stream care, when you think of plant matter entering a stream, you wouldn't think it affected as much, but the grass clippings decompose in the water and can cause a drop in dissolved oxygen and can also add phosphorus to the water. A similar situation of PiO7 was noticed in Centerville a couple years ago. But unlike PiO7, which was very stagnant, not moving, very overgrown, the site in Centerville had some very strong, like high flow and was able to flush all that out. So the downstream sites were affected. This was remedied though by a past stream team going to the lawn maintenance workers at that site, and they implemented a natural buffer by not cutting it so close to the stream, which allowed it to heal, and DO was able to level out and remain healthy. So by cutting further downstream or further away from the stream, you leave a natural buffer to prevent grass clippings and plant matter from falling in the stream, and you stop yourself from causing stress to marine ecosystem. Yes. Our segment of the presentation focuses on restoration sites in Manitowoc County. These sites have underground projects aimed toward restoring the natural flow or streams. In Manitowoc County, these sites are categorized into 2 main groups, urban and rural. Today, we'll be comparing phosphorus, ammonia, and E. coli levels throughout the urban and rural sites and compare the data we collected in 2022 to the data that we collected in 2021. The key difference between our urban and rural sites is location. The location surrounding the stream has a profound impact on the overall quality. With our urban sites situated in the northern part of Manitowoc County, they are often surrounded by wooded areas. They also flow along major roads behind the Lincoln Park Zoo, and they even attract people to engage in popular water-based recreations such as kayaking. On the other hand, Centerville flows through a predominantly rural and agricultural region in the southern part of the county. Here, the landscape is characterized by farmland, with the creek meandering through wooded areas, wetlands, and often through open fields, all while being near roads and bridges. This rural setting exhibits a different set of influences on stream quality compared to its urban counterpart. It's important to note as well that there will be differences in rainfall between the two because of this difference in location. Let's take a look at our urban or garden sites. These sites have been found along the Little Manitowoc River, which flows through Indian Creek behind Lincoln Zoo and ultimately empties out into Lake Michigan. Our 4 monitoring sites are Alamo 5, Alamo 3, Alamo 2, and Alamo 1. Collecting data here is really important because the stream connects directly to Lake Michigan. Factors such as runoff, land usage, and various pollutants can significantly impact the overall quality of the stream.
Throughout our noted observations of the Little Manitowoc River, here are some of the ones that we found to be the most common. Among the animal-related observations, we've noted the presence of goose poop, snails, deer tracks, feathers, trapped fish, a variety of birds, scuds, frogs, and minnows. Regarding the vegetation, we've observed biology growth, exposed roots, aquatic plant life, submerged branches, various types of flowers, duckweed, and overall flourishing plant life. Onto the rural sites or southern sites. Located around Centerville, near County Highway BV, and flowing through Centerville Park, we have 3 monitoring sites, Sierra 3, Sierra 2, and Sierra 1. It's important to recognize that Centerville Creek's location in the southern part of Manitowoc County introduces distinct factors that influence the data we collect and the overall stream quality. These factors may differ from those affecting our urban sites. The goal in Centerville Creek's restoration is to turn the creek into a meandering stream and gradually transform the area into having wetland characteristics. One form of aid in the restoration are wood structures that will provide a stable environment for both plant and animal life to thrive. Recurring observations in Centerville Creek include turbid water with algae growth along the edges, bubbles on the surface, stagnant conditions, surface fill, and a presence of both dead or dying algae and algae mats. Additionally, we've noticed consistently large plant growth in surface biofilm. Now onto our graphs. For phosphorus levels, we've noticed consistently between Little Manitowoc and Centerville that Centerville is obviously higher due to its rural location, but Centerville is constantly over the water standard limit of 0.075 milligrams per liter. The only LMO 5, the farthest upstream site, and LMO 1, the farthest downstream site, never go above that limit. The levels of phosphorus in water are known to stimulate plant growth. This phenomenon occurs because phosphorus is a vital nutrient for plant development. This is shown in these photos of Sierra 1 from the beginning of the summer and the end of the summer. As well, it is crucial to note that excessive phosphorus can lead to detrimental consequences, most notably the proliferation of algae blooms. These algae blooms, fueled by an abundance of phosphorus, can outcompete other aquatic plants and ultimately dominate the water ecosystem. The consequences of these algae blooms can extend further. They can have adverse effects on water quality, reducing clarity and oxygen levels. Furthermore, when these algae blooms eventually die off, they can lead to oxygen depletion as they decompose, harming the surrounding aquatic life. In essence, overabundance can trigger ecological imbalances and hinder the overall health of the water environment. These 2 graphs show ammonia levels for the urban and rural sites. The purple shows our averages for the norm collection, and the gray, this purple, I'm sorry. The purple show the averages for the normal collection, and the blue show the averages for the rain. The x-axis shows us the locations of specific streams, and then the y-axis tells us the average ammonia level measured by milligrams per liter. And the water standard is 0.2. What we noticed when comparing the ammonia levels between the urban and the rural sites was our average. Centerville saw much lower levels. Little Manitowoc showed higher levels of ammonia than after rain events, specifically LMO 1 and LMO 2 showed significantly elevated ammonia levels in comparison to the other sites. Most sites had an average ammonia level at or under the 0.1 standard. And LMO 1 had the highest average ammonia level over all of the other sites. This is also the site that is closest to Lake Michigan. Ammonia is another vital nutrient for plants, including algae. When there's an excess in the water, it becomes a readily available resource for these plants. Algae, being highly effective at nutrient uptake, can capitalize off of the surplus ammonia while competing with other aquatic plants. Like we mentioned before, with elevated phosphorus levels, high ammonia can lead to algae blooms. In summary, excess ammonia can disrupt the nutrient balance in aquatic ecosystems, triggering the overgrowth of algae with adverse consequences for water quality and aquatic organisms. These two graphs show E. coli levels for the urban and rural sites. And here, pink line represents the E. coli collected with a normal condition, and the blue line represents the average E. coli for rain events. And x-axis is again for these specific sites, and y-axis is for the E. coli level, which is measured by MPN, or most probable number, per 100 milliliters. The water standards are 0 to 234, which is considered open, 235 to 999, which is advisory, and anything above 1,000 is considered closed, which we can see with these lines. 0 to the yellow line is open, the yellow to the red is advisory, and anything above that red line is closed. What we found when comparing E. coli levels between the urban and rural sites was all sites had an average E. coli level that met or exceeded the advisory category. Most Little Manitowoc sites were under the standard for closed. All Centerville sites met and exceeded the closed standard. All rain events showed a higher average than normal collection. And overall, Centerville had higher levels of E. coli compared to Little Manitowoc. If we look at our previous observations, we can see that there is a lot of wildlife activity going on at both these sites, but because Centerville is located in a predominantly agricultural region, and Little Manitowoc is not.
Now we're going to compare the data we found for phosphorus, ammonia, and E. coli at the restoration sites in 2022 with this year's. This analysis will provide us with valuable insights into the effectiveness of the restoration efforts and how the stream quality has evolved over the past year. Graphs compare both the 2022 and 2023 data while still comparing the rural and urban. For Centerville Creek's phosphorus levels, for the most part, they have increased within the last year, while Little Manitowoc has decreased. And overall, the rural sites were all above the urban sites both years and have stayed consistently higher than the water standard, which is shown by that red bar.
These are the four graphs that show ammonia levels for the urban and rural sites from 2022 to 2023. And you can see the water standard is this red line. And just as a reminder, the purple is for our normal collection and the blue is for our rain events. And again, these sites and the ammonia. And then what we observed with the ammonia levels from last year to this year was lower ammonia levels for Centerville. Little Manitowoc saw higher levels for rain events this year. Some sites in Little Manitowoc saw a slight decrease in some of the levels, and some saw a slight increase. But overall, there were similar trends across the 2 years. These are the four graphs that we have to compare E. coli levels from the urban rural sites from 2022 to 2023. And the plan again is for the normal collection, and the blue is for the rain events. And 0 to the yellow line, that is the open. The advisory is between these two lines, and over the red is closed. What we observed with E. coli levels from 2022 to 2023 was we saw a slight decrease in E. coli this year for Centerville. There was a significant decrease in E. coli levels for rain events in Little Manitowoc this year, but E. coli levels for Little Manitowoc in the normal collections did increase from the previous year. Alamo One went from being open in 2022, as you can see here, to exceeding the closed standard this year. Overall, Centerville stayed above the closed standard for both years, so above. For the observable differences between the 2 years, at the Centerville restoration, the farthest upstream site, there was an abundance of thriving plant life that was not seen last year because this year they discontinued the use of a herbicide. And then also we saw an uptick in plant growth in the midpoint of the restoration. And finally, there was a concern at the farthest downstream site due to erosion along its shoreline. This year, what we observed with the Little Manitowoc restoration, what sites were more plant growth at Alamo 3 and Alamo 5, which are the most upstream sites in the Little Manitowoc River. And we also saw an increase in algae at Alamo 5, which Alamo 5 is the most upstream site. And as we previously mentioned, algae blooms can have a devastating effect on water quality and stream life. Some notable takeaways are reflecting on our data comparison between the 2 years, where the rural sites are consistently showing higher levels in phosphorus and E. coli. The Little Manitowoc site showed reduced levels of phosphorus and E. coli, except for Alamo 1, the farthest downstream site, which increased its phosphorus levels from last year. This could be due to backflow from Lake Michigan. And lastly, this comparison shows that the restoration sites are stabilizing.
All right, and now on to our 2022 versus 2023 comparison data for all the sites. So first, we're going to be taking a look at the Centerville sites. So, first of all, I know that this is a lot of bars, and it might be overwhelming. Don't worry, I'll explain the trends and what they're asking. The most important thing to remember these is that not every single individual bar matters. Instead, it's important to look at the overall trends. So this chart here on the left shows a breakdown of each Centerville Creek site from the North Branch upstream to downstream towards the lake. While the chart on the right shows the overall average phosphorus levels at each of the sites from the South Branch, from upstream to downstream into the restoration and then into the lake. As you can see, light and dark green bars represent the 2022 and 2023 dissolved phosphorus levels. Lighter green, 2022 data, darker green, 2023 data, and that's for dissolved phosphorus. And then light and dark orange is for the total phosphorus. Remember, dissolved phosphorus is what can be readily taken up by plants and aquatic life, and total phosphorus is just, like Chris said, everything that's in the stream. As you can see in almost every instance, there is generally more phosphorus this year in this in comparison to last year at the Centerville Creek sites, with the rare exceptions of CN11, CN10, and CSO. While the cost for this increase, the general increase is unknown, we speculate that it could have something to do with overall different rain patterns this year compared to last year. Whatever the reason is, it will definitely be interesting to and useful to monitor the phosphorus levels in the years to come. Another interesting observation that we found is that the restoration sites after the confluence, so after the restoration, so basically all the sites that start with CR, so it's these three here, which is same data here. They all have overall lower phosphorus levels than the North and South Branch sites upstream of those areas. It's a trend that can be noticed in the data for both this year and last year, which suggests, once again, that the restoration project has been helping to reduce phosphorus before it can reach the lake. I'd also like to quick say that we do have some more charts for Pine, Little Manitowoc, and Calvin Creek in the same style, but because of the restoration and the importance of these, we decided to put separate charts for this part. So the slide shows, again, two separate graphs. The one on the left shows the total phosphorus at each site. So this is all the sites averaged out total phosphorus levels, from 2022 and 2023. And, compared, and the one on the right is, once again, it's dark green, light green and dark green, stand for dissolved phosphorus from 2022 and 2023. In both of these graphs, you can see that Calvin Creek had the greatest overall phosphorus increase with almost 2.15 milligrams per liter dissolved phosphorus gain. So that's a pretty big disparity there. And approximately 0.2 milligrams per liter total phosphorus gain, which is kind of a lot compared to the others. Little Manitowoc, pretty easy to tell, very similar values this year and last year. That's it, I'll hand it off to Chris.
Thank you. Don't worry, I'm not here to talk about lifestyle anymore, but I am here to kind of give you the key takeaways of all that we've talked about today. Starting with phosphorus levels have decreased within Centerville Creek restoration area, but have remained above those threshold levels. In addition, algae production influenced the dissolved oxygen throughout Centerville Creek. These are related, as with everything we've been talking about is. High phosphorus and low dissolved oxygen levels in Pine Creek supports the need for upcoming restoration projects. Our rural land use, example being our Centerville area, streams showed high phosphorus and E. coli, whereas the urban land use in areas of Little Manitowoc sites have showed ammonia as the main concern. When we compare our 2022 to 2023 data, we see that both total and dissolved phosphorus measures are higher than last year. And this year's phosphorus data and TMDL show that restoration is working by lowering the phosphorus output into Lake Michigan. We can't drive that home enough. We have to keep saying it because it's so exciting. Now, what about the future? What do we look at next? Well, since stream restoration projects are working, monitoring still needs to be continued to ensure the quality of them, to find out what these new needs might be over time and continue to meet them. The data that you've seen today and any future data collected will be continually used as management strategies are implemented in the TMDL and 9 key element plans. Now, we want to make sure that we acknowledge our partners and again, give out those acknowledgements to Amy Lentz and Jim Kettler, who are part of the LNRP and everyone within LNRP, Russ Tooley and the Friends of Haifa Bay, in addition to our funders that otherwise we would not have been able to get paid for what we did, and which would be the Wisconsin Sea Grant, Wisconsin DNR, West Foundation, UW Green Bay Research Booster, National Science Foundation, Bluestokes, Alliance for Minority Participation Program, and the Fund for Lake Michigan. In addition, our thanks go out to professors Rebecca Adler and Richard Hine as our mentors, and Mark Zygmunt, James Zukowski, and Tammy Schultz of UW Green Bay, Manitowoc. So with that, if it works, it'll work. There we go. You no longer have to hold your phone.
Anybody have any questions for us?
Not standing.
I know, I feel like, excuse me, I feel like I should know this. Also, well done, everyone. I felt bad. I was like watching the presentation so closely. I'd like look down at the Zoom and be like, oh no, I gotta. I was just curious when you were talking about pH concentrations, why you bothered including the to the first power.
Sometimes we just don't have an answer to these things. It's one of those times.
That may have been an editing thing.
Sure, not a big deal. I just was wondering if I was like, oh, that's kind of cool. All right, good start.
Since restoration seems to be even the whole thing from what you said, like what amount of money and time and energy goes into a restoration? And is any of it funded by the DNR or how does that happen?
We can't really answer that. question.
Yeah, I mean, I can speak on it a little bit,
Well, let's just stick on that one.
like a lot, I mean. No, it's really, it's a super involved process, I think. Like, the first step would be, identifying, hey, here are where with some of the research and the data collection that they're doing, here are the areas that are best to target for restoration. Then you have to, if they're grant funded, you write a bunch of grants, which takes a long time. You also have to usually you have to write more than one grant for the same project, for all sorts of different reasons. One of them being these projects are pretty expensive. And then the DNR does ultimately fund, restorations, not all of them, but some of them, at least for LNRP and I'm sure other organizations as well. What were the other parts of the question?
Well, that's fun.
Okay. Oh, something to say.
There are direct costs, so you count there are also, for example, if a dam has to be removed. You've got to go to the community and talk about the history of the dam, mill pond, and get people first to understand why the dam ought to be removed. And then there's the public education, which could also qualify as well. So has to right first grade and let the granting agency, be it federal or state level, or even some of the private foundations, West Foundation, understand that we can not only get the money and receive it, but that we can utilize that money in an intelligent way. That's why this program is brilliant. Not only do we get the work done academically, but we also are training future scientists. So the return on that investment is beyond the direct costs that I think was at the core of your question. But I wanted to point out that nuance, which is so critical, and that's why all of you are here. We're so grateful. And I'll turn it back over to.
What I think is really interesting about the stories that they picked out this year, it actually got back to that question, that heart of the question, because when we were approached in 2010, before Centerville Restoration even started, Jim Kettler said to us, we're investing a lot of time and money in this. The Village of Cleveland is investing a lot of time and money on this. We're trying to get these grants and show that this is important. But so we need to do this data collection because if we're going to invest this money, we need to know if it's worth a worthy investment. So what I think is super cool is I think the Centerville data and the Little Manquoc data, that yes, these are worthy projects. And you also you can't restore every stream. It's not feasible. So you have to put those efforts where they're most needed. And I think their Pine Creek data shows that, yes, that was targeted by our county soil and water and other groups as an area of concern. And their data does back that up, that we're making a good choice with those efforts. So it was really exciting to see that when they put all that together.
And I think to more directly answer your question, I believe the Centerville restoration was around $2 million. But the more that you can collect data that shows it has a really significant impact on water quality, the more partners you can bring into projects like that. And they don't all need to be very large restorations. So some of the work that's going to be going on in Pine Creek is actually a collaboration with agriculture to create what are called harvestable buffers. So they're basically special crops that are planted streamside that aim to catch runoff before it gets in the creek, and then the farmer can harvest that for a profit. So as harvesting goes on, you're removing the phosphorus from the system completely. So some of these really creative, novel, low-cost projects we're pioneering in this county, which is pretty cool based on the data that are being collected.
Thank you, great question.
I'm not picking up, somebody else. I think I've got stuff with this up.
And what for the nuts and bolts of the restoration site that were needed? Was it the dam removal and then vegetation establishment? What was the?
Centerville?
Yes.
Yeah, so I don't know if Amy wants to talk about that, but basically, yeah, that was a little bit more inside with LNRP, but my understanding of the project is that it was a complete re-engineering of the stream. So the dam was removed completely. I can't remember how many million. cubic yards of stuff. Sediment were removed. They created the dune and swale system on the other side of the highway, close to Lake Michigan. So that was repurposed. And then the plantings have gone on in several waves. I think it's been 3 separate waves of planting of vegetation throughout the area. Which has led to, yeah, so the stream was completely re-engineered, with those, logs, riffles, the meandering nature of the stream was restored.
And some invasive controls as well.
Yeah, that's what
We're very interested in native species. We recognize these invasives are pretty competitive. And so that was a smaller part of that
Yeah.
equation as well.
yeah,
We do have a picture from before the construction started of our one intern back in the day, standing in Centerville Creek in what's now called the restoration area. He was about 6 feet tall and he's just dwarfed on either side with the banks in that sediment that had built up, and you can just see the erosion that's happening. So it was a very, very major project. They did a lot of work, and it's really cool to see that investment paying off.
And had to have the support of the municipality of.
Yeah.
Yep.
I mean, that's key as well.
Yep.
These partnerships are incredibly important.
Anyway, so.
lots of hands, so.
He's not.
Well, I did.
Yeah.
No, I just looking at the data and I'm a scientist-y person, but my daughter's up there. No, it's just very obviously compelling looking at the data and seeing you can, even a non-scientist, see what that means. So what do you do from here? Now that you've got this data, what's the next steps?
We basically pass it off. For ransom to come back for another year, like, try new things. Come back again. So from our standpoint, you heard about, we will continue to monitor as long as we have the support to do that, because these are long-term projects and we're excited to see as some of the native plantings establish and other things, what's going to happen. You heard about the fact that we have several different restoration or management strategies that are going to be employed on Pine Creek. We're excited to see what happens there. So, our goal is to keep doing this as long as we're here at UW Green Bay, because the joy it brings to us, not only to see the results from the data, but these guys. I mean, this is why we do what we do,
Yeah, and you're gonna get a sneak peek, in some of our concluding remarks, but, yeah. One of the goals of the project moving forward is to engage all of the stakeholders in discussions about, where we want to put our efforts in the future. Lakeshore Natural Resource Partnership really has that community reach. And working with Manitowoc Soil and Water Conservation Department and other partners in the area, agricultural industry, really you have to have those conversations and decide what limited resources where they'll have the greatest effect. It's also informing a couple of really important projects that the students just touched on. The total maximum daily load project aims to quantify phosphorus inputs from the various sources, set targets for reduction so that people have really specific targets to reduce that phosphorus input. So that will be moving forward, will be implemented, and the monitoring will provide data for how well we're reaching those limits. And then the 9 key element plan's goal is to implement a lot of these smaller restoration projects and gauge the effectiveness as well. So the ongoing monitoring is important, but the tweaks that we do to the system and then the monitoring to make sure that they're working really drive that moving forward.
Can I add a little bit to the local answer? Policymakers, we got to get this information to policymakers, because this is also dependent on policy. And then funders, I love what you said, is the money being well used? What does it have to do for the Great Lakes writ large, let alone our communities where we enjoy these streams? And so there it goes from here, it goes all over, it's the ripple effect, if I may, of where it goes, from policymakers to the communities, to the academic, to the continuing research that has to happen. to the people who might fund it, and ultimately, where does it go? To the next couple generations who live here on the shore of the Great Lakes. It goes to kids who aren't even born. So those ripple effects really go, but here's where it starts.
I know there were more hands.
I have a question for you all. If you could, you spent a lot of time in the landscape in these watersheds this summer. If you could pick one project to put on the ground, what would it be and where?
Question.
You can all answer it, or just one of you.
You clearly like.
Maybe you can't pick one of the watersheds? Like, what would you do?
Yeah, like if you had a,
Store it, yeah, a restoration project, is there something that stuck out? I mean, you talked about stream restoration and we know that it's working. Are there other things maybe higher up in the watershed that you noticed where improvement could be made that you think would have a positive impact on the water?
I think probably CS13, so one of our more extreme, the southern center, which I don't know, like, what to do. But I think that that would be good to this time.
And the good thing about, like, the good news about it is, by the time it gets to the restoration, it's fine. Like, it's not inputting into the lake, but like, for the life in that church, that cuts. Yeah, I agree with that.
I like nesting.
Yeah. We didn't really touch on it too much, but CS13 has been a problem child for the children. Since last year, and this year it kind of had more because of the sediments on like 2 of the days, 3 of the days. It was kind of pushed through and just making the stream black. And I mean, it was metal. There's a reason it's called like it's a rough one. There's a couple out there that we are like, oh, we could touch on this, we could touch on that. We don't have, as Sam said, like a proper idea as to what we would do. We're learning about that, which is great. But yeah, I think CS13, 100% the.
And which creek is that on?
Centerville South Branch.
That's like basically the newest upstream on the South Branch.
The hot spot.
Has a picture of
Yeah, we're looking really murky, and basically when you go to that site, you park on the side of the road, there's a farm or two nearby, but then it's a very steep slope from the road and all of the surrounding homes and fields down to that stream, so it's been, I mean, they're not wrong, it's been a problem for a long time.
I mean, if there's things from the nearby farms,
Was it?
are there problems from the nearby farms from runoff or?
We're not sure where, if that's the source, if it's just because it does go stagnant and we're seeing some decomposition. We definitely do know there's high levels of bacteria, which might indicate some runoff, but we're not entirely sure exactly where it's coming from. So, good question though.
Russ.
Sure. I'd like to ask each of you,
oh boy.
now that you spent the whole summer going through rain, nettles, etc., are each of you still interested in field research and science? And was there something that surprised you during the summer?
Okay, I can start. Yes. It does get pretty sprinkly out there. You really need to learn to wear the pants, even when it's like 95 degrees. It kind of sucks, but it's all kind of worth it. And it's really fun, and I feel really smart. But I get to call myself a scientist, and it's really cool investing in the future because, like, I'm not gonna technically see the results of everything in my lifetime, but when I have kids and they have kids, and I hope that I'm doing something good.
So I really enjoy the research and seeing the data. Sometimes doing the field work, I enjoyed it, but when we would go out, we were in the car, we were all like talking and having a good time. And then 4 hours later on the drive back, it was just completely silent. We would do our lab stuff and no one would talk at all. It was just like exhausting at some points, but still seeing this data and then looking back at it and analyzing it, it's really fun and exciting. And I want to do research in the future. So it was really fun to get a sneak peek into it and know that I really like what we're doing.
So I feel like my group was the northern side. We went out in the morning. And so waking up and getting in the car, my experience is kind of the opposite. We were, Chris was talking, but. And so, after a little bit of time, you wake up more, and then I enjoy going out in the field, especially with this group of people. And so personally, I enjoyed the lab more. Not that I didn't enjoy the field, it's just I'm more drawn to the lab, working with the different equipment, learning like I've never been in a lab and done all the different things that we had done before. So it was great to get that experience. And now I kind of know in the future with any career that I pick, I know that I would love to work in a lab because I now have this experience from this. So.
This was my first time like working in or doing anything similar to this, and I really liked it, both the field and lab work. I definitely preferred the lab work because the field was really hot out and it was rain and stuff, which wasn't too fun some days. But I really enjoyed all of it overall and to continue doing stuff like this.
2 years, I have fallen in the water from the top of a bank. I have been completely covered in thorns and like every little bit of stinging nose you can. On camera, I've dumped water from my boots time and time again. A lot of people have done that. And I would do it all in a heartbeat. I love being in the field, and my baby of going out and getting the phosphorus load calculation data. That was my excuse to be like, hey, you guys do the lab. I trust you guys. Like I legitimately, we all trusted each other. It was amazing. And I would just make out 2 people, it's like, what's going on field? What's going on field? Anybody, please, anybody. I need 2 people with me to make life easier and go out, enjoy it. It was a great time. I would be out in the field 2 days a week instead of always in the lab. And it was just in a heartbeat. I love the field research portion of it so much, despite any of that pain.
So this is also my second year, like Chris and Sam, doing this, and I really wanted to come back because I absolutely love the research and stuff we did with the collecting data and just compiling it all into these presentations and making those connections to everything was so much fun. But I absolutely prefer the field more than the lab. And just being outside and just enjoying that environment with people that are super fun to hang out with and everything just made my entire 2 summers. And I hope that when I start my career after college that I can do that kind of field work again with a good group of people.
I would say, yes, I honestly don't know which side to take in the lab versus field. No, the field is super nice, you wake up really early in the morning, get up at 5. Night peaceful drive, sometimes get to see like darker out, kind of get to see the sunrise over the lake. It's just beautiful. Then go collect samples, super peaceful you're getting to hang out by all these streams, seeing all the wildlife, waking up in the morning. And then you get back to lab and it's just utter chaos at some. But I mean,
still battles coming.
Full shooting left and right, all summer. Interesting.
So 2 things actually. One thing we don't have a slide for, but we just found out from the professors was our first day out before we even started collecting. We got to one of our sites on Calvin Creek in CA03, and the entire stream smelled and looked like milk. It was pure white. We never saw it before us veterans. We were like, what the heck is this? Well, we just got confirmation from the professors tonight that it was indeed a milk spill, but it got cleaned up because it was reported so fast. So it didn't have any negative impact on the actual stream. But the other
surrounding farm. There was a farm that was upstream of that site and it was just an accidental spill. So,
which is what we predicted. Try to get it down or anything.
it's like, well, why is this room?
We drove all summer. Pass milk check, pass milk check, pass milk.
That's what we call, we have nicknames for most of the sites. Then the other thing, if I can flip to it real quick, was this really weird thing that happened with PIO 6 all summer. We don't know why this happened. We tried testing for it. So when we got our samples, we have to put them in an autoclave after we treat them, and that just heats them up to a very hot temperature. And every time PiO6 came out, it was orange. And sometimes it had this weird little precipitate you can kind of see in this one, and other times it didn't have any, but it was very vibrant and orange. So our guess for it was that it was an iron reaction. So the professors got us these test strips that we used when we went out to the field to test it, and it had some level of iron content in it over the summer. And then when we tested, when it came out of the autoclave, when it turned orange, it had no iron content, but we still don't know why it happened or what caused it. It just went over all summer.
Check whether shoes like Fisher Character, Point Character.
So we had done, both Fisher and Point until last year. So yes, we have the data going back several years on those two. The only reason we're not doing those currently is because we do have a lot of data in conjunction with some data that's collected before we even came on board. And even with 9 students, we only had so many resources and we were limited with supply money. But one thing we do is, Rick teaches an environmental science lab and we both team teach an ecology lab, and we'll go out to a lot of those different streams and incorporate some of this work with our classes. So we still do try to get to those as well. Yeah, they're all really important and they all have their own unique, it's really interesting. When we first started this, we thought, well, they're so close together, the same area, they're probably all the same, and they're not. They really all have their own unique personalities, if you will.
At some point, you think you might do a more biological diversity, data collection? What you're doing is brilliant. I'm worried. It takes more resources, of course.
Yep, we're actually doing that with the classes.
Yes.
So, yep, so these guys, have their hands full, doing some of the analysis, especially the phosphorus analysis takes a lot of time. So there's just a capacity issue with the students over the summer. But that's where the class-based work can come in. So we do a simple diversity index with the environmental science class. And they have been doing Centerville and Little Manitowoc River. So they've sampled 4 sites on those 2 creeks. And then Becky with ecology, and I'll take over halfway through the semester, are doing a couple of real diversity series to look at invertebrate biodiversity in those areas. So we'll get a couple snapshots.
And as we expand this and expand the environmental science major, we'll probably be incorporating hopefully some students who need independent study credits and things like that. And those are those perfect places to put students in. So we're looking forward to that as well.
If you guys have been collecting data since 2010, has anybody looked back at all of that data and compared, okay, so this is where we started, this is where we've gotten to? Is it the same? The restorations, year over year, you can see it's better, but how about the sites that haven't been restored? Are they changing? Have you noticed anything?
What we have not had a chance to do, sit down and really do some strong statistical analyses, just again, time capacity. But we have looked at some of the trends and we can speak to that. What I think we've noticed there, those non-restoration sites tend to be much more variable year to year and the restoration sites were as well in those early days because, they were bare soil, you were doing planting, there was disturbance. And really it was in the last 2 years that they showed, that's the first time we saw really that stability. So that's my main impression.
Yeah, and the other, so again, we have not done the long-term statistical analysis. But another hypothesis that we have is the problem is not just surface runoff. So they're measuring the total phosphorus and the dissolved phosphorus. Total phosphorus tends to come in with surface runoff. So you get a lot of particulate matter washing in over the landscape. Dissolved phosphorus is a very large problem in most of our creeks. So we see the largest portion of the phosphorus coming in the dissolved form which suggests it's probably not surface runoff, it's probably subsurface runoff. So when we look at management decisions, you have to account for both rainfall events, but also some of the subsurface flow as well. So yeah, that long-term analysis, but it is exciting that in the beginning, the restoration sites look the same as all the other sites on the premise. And as that restoration has matured, we're starting to pick up the fact that it really is making a difference. Yeah, great question.
Thank you.
If anyone's a statistician and wants
Yeah.
a long-term data set.
Yeah, we got that. Yeah, that's the data. We can talk about that in a bit when we kind of do our wrap up. Questions? You've all been such a great audience. We love you.
Looks like it's about time to wrap
All
up.
right, well, we just have a few more things, so we won't keep you too long. We just kind of want to summarize our experience. I think y'all are, I don't know what you guys are looking forward to.
If anyone wants to stick around and talk to our research students, I'm sure they'd be happy to stick around and have a chat, so, you want me to start?
Yeah, with all the problems.
Yeah, so basically, I just want to wrap up really quickly by reiterating some of the really important points that I think, bring value to this project for me. Ross mentioned the Wisconsin idea, and that is the reason Becky and I both became involved in this project, because we don't want to collect a data set that we're the only ones that see. Really interesting scientifically, but doesn't ever get used. Our goal from the beginning was applied research. So we wanted to gather data that were going to be used right away. The data are all publicly available on Lakeshore Natural Resource Partnership website. And thanks to Russ for being our data guru. Takes all the numbers that these guys collect and make them available in real time. So basically.
Yes, I have a number I will share, I promise.
Yeah, so we want those data to be out there to be used by anyone who wants to use them. And we want to move forward, and the partnerships that we're developing with a lot of our community members, profits, nonprofits, government groups, are really, really important. So we want to move these conversations forward and try to identify areas where we can really have an impact on improving water quality. Finally, I guess, I will say that one of the things that really is exciting for me is that this is a project where students gain actual real experience. So this is not a classroom mock lab. We can put those together really well. We can teach great things with a cookbook lab or even an open-ended lab. But this is a problem that we don't have answers to. And that makes it particularly interesting and difficult, but gives them real world experience. So here's this issue, let's try to figure it out. And let's use the data to try to explain what's going on. And that connection to a format like this is super valuable for the students as they try to explain what all these, how many numbers?
5,000 or more a year.
5,000 numbers mean to an audience, and they have done an outstanding
They
job.
have.
So that's what I wanted to say, but then the impacts go beyond just the.
Yeah.
So
About, so this partnership again started with us and Jim Kettler from LNRP saying, what are we going to do? It started small and, as we said, expanded. Recently, I had the opportunity to put some numbers together. So the first thing I want to say, to Rick's point of it being real world, I'm looking at the students and smiling because we know how frustrating it is for them. They come to this project and they're new, right? It's week 2, week 1, sometimes they're sampling on their own. They come to lab meeting. Well, what's this orange stuff mean? And we look and go, oh. So, you know, they really have to figure it out for themselves. And as I said in the beginning, this was their baby, right? They came up with these stories. They did this analysis. We guided them, but it was really all them, and I couldn't be more proud. In terms of this, kind of the broader impacts of this, the importance of supporting this, I feel a kinship to our Centerville Creek and other creeks, because I've heard people, you know, in the past say, you work on those small creeks, they can't have that big of an impact compared to the Milwaukee River and the Manitowoc River and all these. Well, you saw some of the numbers on phosphorus load that Chris presented, right? Small can be mighty. And here we are, a small campus, local campus. We serve our community. And here are some of the numbers. So since 2010, note that in 2020, COVID shut us down like everything else. We did not have a research program. We have had 51 undergraduate student interns, 51 from this campus and now from Green Bay. Most of those were freshmen and sophomore students. We now have high school students, so that's amazing. Presentations like this, but also our students have presented at regional meetings in Madison, in the state capitol, where legislators come and see the work. They presented at national meetings. Presentations involving undergraduate authors related to this work, 59. So, data points, I'm a little off, I'm short because I couldn't get back to like our 2012 on data. We had stored that somewhere else and I can find it, but I was doing this on the fly. So, to Russ's point, over 45,000 individual data points. And we had talked about money, to support this project. We couldn't have done it without LNRP, community support. But we also have been able to leverage this to working with some of those other agencies that you saw. And freshwater related grants that are external, not counting the support that LNRP and some of the homeowner groups and stuff have given us, over $400,000 coming to our community to work on freshwater. So we couldn't have done any of that without the students and without all of you. So we're just really grateful and really proud of what they've been able to accomplish as a collaboration, like Rick said.
Yeah, and ultimately, like, to have community that is interested in the environmental issues that are going on is really the key. And that drives the whole thing. So we thank you for showing up tonight. Thanks for your support and have a great evening.
Robert,